Alright, in this video we're going to take a look at another trigonometric equation that we're going to solve. And this one's pretty complicated. We're going to have to use a trigonometric identity to make a substitution here, and then from there be able to go ahead and solve the problem. Alright, so I've done a series of videos now on solving trigonometric equations, and they're kind of, if you go along in order that I'm making the videos, they're getting increasingly more difficult as we go. So if you haven't seen any of those yet, or this is your first experience ever with solving a trigonometric equation, I would advise you to maybe go back and watch the first one that I did of solving like a real simple trigonometric equation, and then kind of work your way up to these more difficult examples. Alright, so this one here, we have sine of 2 theta minus cosine theta equals 0. Alright, couple problems with this equation that are not going to allow us to solve it unless we make some kind of change or do something different with this. Right, first, I have two different trig functions, a sine function and a cosine function. If I have the two of them mixed together in the same problem, it's going to be really difficult to solve for that variable. The other thing, my angles, one of my angles is a 2 theta, the other one is a theta, a 1 theta. Right, so if I have two different angles inside my trig functions, that's going to be another layer of difficulty in trying to solve this equation. Right, so what I have to do here is when I see something like this and I see, well, I have a sine and a cosine, that's going to be difficult. I have a 2 theta and a 1 theta, that's going to be extra difficult. I need to do something. I have to change one of these to something else in order to be able to work with this equation. And if you notice, this sine 2 theta, that should look somewhat familiar to you at this point. Right, somewhere, and even if you don't remember exactly what the formula is, you should say, wait, sine 2 theta, I saw a formula for that. There was a formula where it was sine 2 theta equals something, right? That equals something, and I can maybe use that formula to replace this with something else, and then maybe if I do that, I can work my way through the problem, right? And then if you don't remember what that formula is, look it up and figure out what it is, and then use that and replace it, right? So this is one of the double angle formulas, which I did a video where I talked about the double angle formula, so you can go back and look at that if you want to. But sine of 2 theta is equal to 2 times sine of theta times cosine of theta, right? So since I have a sine 2 theta here, I know I'm not going to be able to solve the equation as it stands now with the sine and the cosine and the 2 theta and the 1 theta. Alright, well, this is something I can do, and maybe it'll help me out and make it so I can solve this equation. Maybe not, and I'll have to try something else. But let's try this. It's the first thing I see that I can actually do something to work on this equation, so let's go ahead and do it. Alright, so in place of the sine 2 theta, I'm going to replace that with 2 sine theta cosine theta. Right, and then minus cosine theta equals 0. Right, so I use that trig identity, that double angle formula for the sine function, to replace sine 2 theta with something else. Now, that solves one of the problems that I talked about in the beginning. Right, we had a 2 theta and a 1 theta, and I said when we have two different angles in our trig functions, it's really hard to solve for the variable theta. Well, now when I use that double angle formula, now there's no more 2 thetas, right? Now everything is in terms of theta. So we at least solved that problem as far as having the two different angles in there, but we still have the problem of having a sine and a cosine together in the same equation, and that actually got worse because now I have a sine and a cosine multiplying each other in the same term of my equation. So it solved one problem, but it didn't solve the other one, and it seems like maybe the other one's even worse than it was before. But that does allow us to do something else, and I actually did an example similar to this in one of the videos that I did previously, where we have two terms here, and these two terms do have something in common, right? They both contain a cosine theta, right? So what I can do here is factor out that common factor of cosine theta, right? Remember, when you're solving trigonometric equations, you're not only using trigonometry, right? It's not all just unit circles and right triangles and all that stuff. Sometimes you have to bring back some of the techniques that we talked about when we were learning about quadratic functions and polynomials and things like that. Sometimes you have to use those techniques to solve problems that involve other types of functions, including the trigonometric functions, right? So, all those tools, I liken learning like algebra, precalculus, and trigonometry. I liken it to like just having a toolbox, and like every new thing you learn, factoring and factoring by grouping and greatest common factor and all these other things. They're all just like different tools that you can add to your toolbox. And then as you proceed through mathematics, every once in a while you have to open up that toolbox and like dig down to the bottom to those things that you haven't seen in a while and pull them out and use them in order to solve this other type of problem that you're working on, right? And that's the case of what we have here. All right, so I have this trig equation. where I have two terms, they have a common factor, so let me pull out that tool of factoring out a greatest common factor, and let me use that here. All right, so I can take that cosine theta, and I can pull that out of my expression, and we're left with a 2 sine theta from the first term, and from the second term, it's going to be a minus 1. Right, remember, when we're factoring a greatest common factor and we pull out that entire term, we still have a 1 left behind, right? Because if I use the distributive property and multiply this back into the expression, I need that minus 1 there, so when I multiply the cosine theta, I end up with a minus cosine theta, right? I don't just leave a 0 there, because then when I multiply the cosine times 0, I don't get this minus cosine theta that was there before. Right, so when I factor that out, there's still that 1 left behind inside the parentheses. All right, and what I accomplished then by pulling out that common factor, I've now separated my two different functions, right? The cosine theta is out here, the sine theta is inside the parentheses. They're no longer mixed together, so that took care of the other problem that I saw at the beginning, that I had those two different functions in the same equation. Because once I factor this, I can separate those two factors, right? I can say cosine of theta is equal to 0, and I can say 2 sine of theta minus 1 is equal to 0. Right? And now I have two separate equations, but this one's just cosine and this one's just sine, so it's not a problem that I have one of each because now they're in two separate equations. Now I can proceed and actually solve this problem and figure out my solutions. All right, so when you're dealing with trig equations, these are some of the techniques you have to use. Sometimes you have to fall back on some of your formulas that you've learned or some of the identities that you've seen, and use those to rewrite your equation in a certain way. And then sometimes you have to go back and do factoring or things like that in order to actually proceed and solve the problem. All right, but now when we get to this part, now this should be the easier part of the problem. If you understand trigonometry and if you've seen some of the videos I did of solving the simpler types of trig equations, this is the part that kind of shows up at the end of every single one of these trig equation problems. All right, cosine of theta equals 0. So where does cosine equal 0? I don't know. Let's think about it. Well, I do know, I'm just not saying it. All right, so cosine theta equals 0. Remember, I'm talking about the unit circle. Cosine is my x coordinate. All right, well, where does x equal 0? Well, x equals 0 up here, right? That's the terminal point 0, 1. And x equals 0 down here. That's the terminal point 0, negative 1. All right, both of those have x equals 0. And remember, the definition of the cosine function is it gives me the x coordinate of the terminal point on the unit circle. All right, so this angle up here on the positive y-axis, that's the angle of pi over 2. I kind of drew this where I need to write the answers here. So I get theta equals pi over 2, right? That's this angle up here. And the angle down here, that's 3 pi over 2, right? And those, at this point of your trigonometric journeys, those should be angles that you just know from the unit circle. You should know that the positive y-axis is pi over 2. And you should know that that is, the point 0, 1. And you should know that the negative y-axis is 3 pi over 2, right? And that's the terminal point 0, negative 1. Those are the points where cosine of theta equals 0. Right? So those are the angles, pi over 2 and 3 pi over 2, where if I take the cosine of those angles, it's going to equal 0. And then, again, hopefully you've seen some of the other videos I did on solving the trig equations. I have to add the 2 pi k to each of those, right, to cover every single possible solution. Remember, every time I go a full lap around the unit circle, which is adding 2 pi to my original answer, I end up at the same terminal point, and I'm going to have the same value for cosine. Right, so either one of these answers, if I just keep doing laps, adding 2 pi any number of times, or in either direction, I come back to the same answer. Right, so that's why that k there represents any integer, right? Any positive or negative whole number, right? That represents just extra laps around the unit circle, but then ending up at that same point. All right, so that's my cosine theta equals 0. Now I have to do a similar thing over here for 2 sine theta minus 1 equals 0. All right, so first thing here, I need to isolate that sine of theta, which means I'm going to add the 1 to the other side and then divide by 2. And if I do that, I'm just going to do that all in one step here. And hopefully you understand that, right? So I get sine theta equals 1/2, right? Plus 1 and then divide by 2, I have a positive 1/2 on the other side. All right, so sine theta equals 1/2. All right, now a similar thing I just did over here. Where on the unit circle does sine theta equal 1/2? All right, so if I draw my little unit circle over here where I have some space to do it. All right, well, for sine theta equals 1/2, I can use my trig hand, right? And if you haven't seen the video I did on trig hand in the unit circle, you should check that out because it makes doing this type of problem pretty easy without actually memorizing the entire unit circle. All right, so sine theta equals 1/2. Sine is my y coordinate. If I put down my ring finger here, above that I have root 3 over 2, that's my x coordinate. Below that I have 1 over 2, 1/2, that's my y coordinate. So it's going to be over here at pi over 6, right? I have the terminal point root 3 over 2, comma 1/2. That's where y equals 1/2, and that's my angle pi over 6. Right, so one of my answers here is going to be theta equals pi over 6. And again, plus 2 pi k, just like all my other solutions, to denote every possible answer, every possible solution to that equation. Right, so it's pi over 6 plus 2 pi k. And then the answer is, well, where's the other point on the unit circle where I have a sine or a y coordinate equal to 1/2? And that's going to be over on this side, right, reflecting this point over into the second quadrant, where we're going to have negative root 3 over 2, comma 1/2. That point also has a y coordinate of positive 1/2, which means that the sine of that angle is going to equal 1/2, because sine gives you the y coordinate of that point. And then it's a matter of, well, what angle is that? Right? And again, at this point, you should be well enough versed in the unit circle to be able to pretty quickly figure out that angle over there would be 5 pi over 6. Right? This one on the right side in the first quadrant is pi over 6 above the x-axis, so it's like 0 plus pi over 6. The one over here, using symmetry, is pi over 6 above the x-axis. Remember, the negative x-axis here is an angle of pi, so it's pi minus pi over 6. Right, which is 6 pi over 6 minus 1 pi over 6, which is 5 pi over 6. Right, so if you don't have the unit circle memorized, you don't know how to real quickly figure out that this angle over here is 5 pi over 6, that's how you can reason your way through it, just by using symmetry. Right, this one's 0 plus pi over 6. The one on this side is pi minus pi over 6. And then if you actually do the math and figure that out, you get 5 pi over 6. And again, plus the 2 pi k to denote doing extra trips around the unit circle and landing back on that same point and getting the same value for sine. Right, so my original equation up here, I've got 4 different solutions to it. Well, actually, I have an infinite number of solutions to it. I have 4 solutions on one single period of the function. So between 0 and 2 pi, I have 4 solutions to this equation. And then those 4 solutions are seeds. Each one of them is a seed to an infinite number of solutions. Pick any one of those points and then just keep doing extra laps, a single lap around the unit circle and winding up at the same point, and you keep getting the same sine values or cosine values every single time. All right, so that's another example of solving a trig equation. The last part of this I went through kind of quickly, but if that didn't make sense, or if I went too fast or didn't quite explain it well enough, I would encourage you to go back and look at some of the earlier videos that I did on solving trig equations, where I did a couple where I solved trig equations where we just started with something that looks like this or something that looks like that. And then I spent 10, 15 minutes just explaining how to get from this to figure out that these are the solutions, right? So if that part I went too fast for you, go back and find those videos where I did the simpler types of trig equations. And you can follow through those and kind of get that more in-depth explanation of what's going on and how we're doing that stuff on the unit circle. Because it is important to be able to do that stuff when you're solving these equations, right? And I'm not done yet. I'm going to do a couple more videos where I do some more complicated types of equations involving the trig functions and how to solve those. So make sure you check out those other ones as well.